Nice.
Okay, hello, welcome back. It's recording, right? Okay, great. So, let's see. So you may have noticed that I've been bouncing back and forth between like lattices and Coxeter groups, and so today maybe that'll make sense because I'm going to prove, or at least start proving, that the weak order on a finite Coxeter group is actually a lattice, so that makes sense for why we've been considering lattices. But let me actually start with a couple of comments. So one will address a question that Ilaria asked last time, and the other will address a comment that Ilaria made after class. So the first thing is, so I want to view n squared. So by n squared, I mean the set of positive integers. Well, by n, I mean the set of positive integers, and by this, I just mean ordered pairs of positive integers. So view this as a poset where the order relation is given by saying that a comma b is less than or equal to a prime comma b prime if and only if, well, a is less than or equal to b as numbers, like as integers, and a is less than or equal to a prime is what I mean, and b is less than or equal to b prime as integers. Okay, so this is some poset, and in fact, it's a lattice, but actually I don't need that here. So I want to consider the set of finite order ideals of this, and my claim is that this is actually isomorphic to Young's lattice. So remember last time I mentioned Young's lattice, which is the lattice of integer partitions ordered by the containment of the Young diagrams. And so I just wanted to remark that Young's lattice is isomorphic to the lattice of finite order ideals of n squared. So I don't want to take all of the order ideals because that would include things like the entire set n squared, and that doesn't correspond to a Young diagram, but it's not too hard to show that this is true. I won't go into the details, but if you want to sort of convince yourself that this is true. And the other comment that I have, so this is the question that Ilaria asked, was, remember I said that so if you have a finite lattice, every element can be written as a join of joint irreducible elements. And Ilaria asked how this fails in infinite lattices. So here's an example where this fails. So let L be, so actually it's going to be the dual of n squared, but I'll just draw what it looks like. So I have this element here that covers two elements. Each of these will cover two elements like this. And then each of these will cover two elements like this. And then this just keeps going. So this is some infinite lattice. You can check pretty easily that it is a lattice. And this claim about every element can be written as a join of joint irreducibles is not true here, because this lattice doesn't have any joint irreducible elements. That's just because if I take any element, I can write it as the join of the two things that it covers. So like, for example, if I took this element, it's just the join of this thing and that thing. And if I took this element, it's the join of these two elements. So this lattice doesn't have any joint irreducible elements, so obviously you can't write any element as a join of joint irreducibles. Okay? Okay, so now let me go back to the weak order. So we had this So let me say, now we're going back to the weak order. We had this proposition that I stated, but now I'll prove it. So for two elements u and v in my Coxeter group, u is less than or equal to v in the right weak order if and only if the set of left descents of u is left inversions of u is contained in the set of left inversions of v. So for the proof, so let's suppose first that the set of left inversions of u is contained in the set of left inversions of v. Then let's let S1 through Sk be a reduced word. For u. And I'm going to let w sub I, oh, maybe I don't want to use w. Okay, let's let y sub I be what I get by taking the prefix of length I of this reduced word. So it's just S1 ... Si. Okay. So I'm going to, so we will prove by induction on I that yi is less than or equal to, in the right weak order, this element v. So first of all, if I is 0, then yi is just the identity element, because I'm taking the empty product. And in that case, okay, this is obvious, because the identity element is less than or equal to everything. So if I equals 0, then yi is the identity, which is less than or equal to v. So we're done. So now let's assume that I is not 0. So now, okay, maybe I'll go over here. Now assume that 1 is less than or equal to I is less than or equal to k. I want to let Tj be this reflection that I get by writing down this palindrome. So this will be S1 ... Sj minus 1, Sj, Sj minus 1, ... S1. Okay. Then T1 through Tk are the distinct elements of the set of left inversions of U. Right, so this is something we've seen before, where if you want to write down the left inversions of your element, you can take some reduced word, and you just form all of these palindromes like this. So by induction, there is some reduced word for W of the form, well, first of all, I should say, where am I using the induction? I'm saying that by induction, y sub I minus 1 is less than or equal to v in the right, oh, sorry, not W. W should be v. I wrote W here, but I'm changing things on the fly because I messed up. But okay, so there is a reduced word for v which is of the form, basically you take S1 through Si minus 1 and then you extend it, because that's what it means for y sub I minus 1 to be less than or equal to v in the right weak order. So this is S1 dot 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 Si minus 1, and then some, let's say S1 prime dot 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 SQ prime. Where here Q is just the length of V minus I plus 1. Does this make sense? Okay, so this is just, again, saying that, so this part here is just y sub I minus 1. And saying that y sub I minus 1 is less than or equal to v in the right weak order, which is our induction hypothesis, is just saying that you can extend this reduced word for y sub I minus 1 to some longer reduced word for v. So since t sub I, so t sub I is one of these palindromes, t sub I is a left inversion of u, and we're assuming that the left inversions of u are all left inversions of v. So since it's a left inversion of v, and, well, we also know that these are all distinct. So t sub I is not t sub 1 through t sub I minus 1. We have t sub I equals S1 dot 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 Si minus 1, S1 prime dot 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 Sm prime dot 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 S1 prime, Si minus 1 dot 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 S1 for some, okay, so I'll say what this is, for some 1 less than or equal to m less than or equal to q. So all I'm saying is that ti is a left inversion of v, which means that I can write it as one of the palindromes that I get from this word. So I basically write down this word up to some point and then I go back. And I know that the distance that I should go in this palindrome should be beyond the Si minus 1, because if I just did like S1, S2, S1, and I sort of stopped here, then I would have gotten one of these. I would have gotten T2. But I'm assuming that it is not one of these I minus 1 things, so I actually have to take the palindrome where I write down all of these, and then I go back up to some point here, which I'm calling M. Okay? So hence, V is Ti squared times V, because Ti is a reflection, so it's an involution. This is equal to, okay, so Ti I can write as S1 through Si dot 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 S1, right? That's the original definition of Ti, like this. But then I can also write it in this way. S1 dot 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 Si minus 1, S1 prime dot 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 Sm prime, S1 prime, Si minus 1, S1. And then times V. This is equal to, well, basically I can cancel things because I can write V in this way. So this is a reduced word for V. And if I sort of cancel the S1 through Si minus 1 here with the S1 through Si minus 1 there, then, oh, and also I can cancel the S1 prime up to Sm prime from the prefix here. So this will be, I'm going to keep this. And then this I can rewrite as so S1 dot 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 Si minus 1, and then S1 prime up to S, well, I'm going to remove the Sm prime, and then Sq prime. So do you see why this is true? Again, all I'm doing is I'm taking this word and this word for V, and I'm just canceling a bunch of things from here and putting it here. And this essentially has the effect of like taking this word and just deleting the Sm prime. That's essentially what this is doing. Okay, but then I can do even more cancellation to write this as, right, so the Si minus 1 through S1 here will cancel with the S1 through Si minus 1. So this will become S1 dot 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 Si, then I cancel things, and then I get S1 prime, Sm prime hat, dot 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 Sq prime. So that's a way of writing V. And this is a reduced word for V. So I should say this word has length. Well, okay, what is the length of this word? It's I plus Q minus 1, because it's Q letters here minus, I took out the Sm prime. So this is I plus Q minus 1. But I plus Q minus 1, according to this, is the length of V. So this means that this is a word representing V, and it has length equal to the length of V, so it must be reduced. Okay, so it is reduced. So we've done sort of a lot of computations with words, but now let me just take a step back and say, what have we done? We wanted to prove by induction that yi is less than or equal to v. Well, yi is just S1 through Si, which is now a prefix of this reduced word for v. And so the definition of the weak order says that yi is less than or equal to v, if and only if we can find a reduced word for v that contains a reduced word for yi as a prefix, and that's what we've done here. So this shows that yi is less than or equal to v in the right weak order, which completes the induction. Okay? Yes, Yinza?
So did what I said, the stuff I said last time, does it work?
I don't remember what you said last
Okay,
time.
so this is my idea.
Okay.
So you assume that TLU is contained in TLE.
Mm-hmm.
So then you know what the exact form of those are. Like in terms of a reduced word and U and a reduced word.
Right.
And then they're
So-
each reduced, right?
Yeah, I guess one issue might be that like you might have like different looking reduced words, but yeah.
But can we do a one-to-one mapping? Like, can
Oh, I see.
because the length is.
Is that maybe what this is doing? I don't know if that's like.
Is it? Well, the length of each of them are the same, right? Sorry,
Length of what?
like each of the words in TLU written in the form that you wrote it, it's reduced, right?
Yes. I mean, this is what I chose, and it was reduced.
No, like the elements of TLU when you write it as S1, S2.
Oh, these. Well. Oh, like this. Like, is that a reduced word?
It is, right? Because we can use Matsumoto's or whatever.
Oh, well, no, I don't think it's going to be reduced in general. Yeah, I think it will not be reduced in general.
Oh, really? Why?
Should I give you an example?
Yeah.
Okay. So I've done one direction of the proof. Let me do the other one, which is pretty short,
Okay.
and then I'll give you an example where this is not reduced.
Okay.
Okay? Okay, so for the converse,
No, I think you're right, because I think if what I said is true, then each word should only have one representation.
okay. Yeah. Okay, but yeah, so the converse is easy. We just say, actually, I don't know if I have to write this down, but if u is less than or equal to v in the right weak order, then I can find some reduced word for v that contains a reduced word for u as a prefix. And then when I find the palindromes, to compute the left inversions of u, each one of them will be one of the palindromes that I could get from that reduced word for v. Right, so the converse is not hard. Okay. Okay, but I can give an example of where this is not reduced. Let w equal, maybe I can just do s, let's do s4. Let's take, I guess my element should be, u is the long element. And here's a reduced word for the long element. S1, S2, S3, S1, S2, S1. You can trust me that this is a reduced word for the decreasing permutation of size 4. And so if I compute the last one of these palindromes, so in this case T6 would be S1, S2, S3, S1, S2, S1, S2, S1, S3, S2, S1. So what is this as a permutation? Let me just do this. Where does 1 go? S1 sends 1 to 2. This sends it to 3. This sends it to 4. This sends it to 4. This sends it to 4. Do you see what I'm doing? I'm just tracking where like 1 gets sent. So this, okay. 1 goes to 2, goes to 3, goes to 4, 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 goes to 3, goes to 2, goes to 1. The 1 gets fixed. Wait, maybe I don't even need to do this. Here's a reason this is not reduced. The long element has length 6. This is a word of length bigger than 6, so it is, yeah, it's not reduced. I could continue this and tell you what this does, just to complete the computation. So okay, 2 goes to 1, goes to 1, goes to 1, goes to 2, goes to 3, goes to 3, goes to 2, goes to 1, goes to 1, goes to 2, no, sorry, goes to 1, goes to 2. 2 goes to 2, and I think, maybe I won't go through it, but 3 goes to 4 and 4 goes to 3. So this actually is the simple reflection S3. So this is very much not reduced because it's actually some long word, whereas actually it's representing S3.
Yeah, I think maybe I thought that all of S1 through SJ have to be different elements, but they're like they're not.
Oh, okay. Yeah, no, they don't have to be different. Okay. So I think today we're just going to do a lot of proving things. I don't know actually if I'm going to, well, maybe I'll get to the lattice property. But for now, let's do this. So proposition. Oh, okay. I successfully deleted the last like 5 or so minutes from the recording from last time. And I realized that this was like actually quite easy, and I don't know why I was struggling with this. But okay, so the maps, x goes to w naught x, and x goes to x w naught, are anti-automorphisms of the weak order. And the map, which is just conjugation by W naught, is an automorphism. Okay, so proof. So I'm only going to prove that this is an anti-automorphism. The same argument should show, just by doing things on the right instead of the left, that this is an anti-automorphism. And if you believe that these are both anti-automorphisms, then you should believe that this is an automorphism, because doing this is just doing this anti-automorphism and then doing this anti-automorphism. So it's like you're sort of flipping the post-it upside down and then flipping it upside down again. So I'm just going to show that one of these, let's see, this one, is an anti-automorphism. So suppose that U is less than or equal to V in the right weak order. So what does this mean? Well, maybe I didn't write it in exactly this way, but this is really equivalent to saying, so equivalently, this is just saying that the length of U inverse V is the length of V minus the length of U. So I think the way I originally phrased this when I defined the weak order was I said, oh, well, U is less than or equal to V if I can find some x such that V is Ux and the length of U plus the length of x equals the length of V. But, I mean, if V is Ux, then x is U inverse V. I can just multiply by U inverse. So really, this is equivalent to saying that the length of this element is the length of V minus the length of U. So this is an equivalent way of saying that U is less than or equal to V in the right weak order. Okay, but now I just know things about how lengths act when I multiply by W naught. So I can say the length of, so I'll write W naught V inverse times W naught U is, well, I can, okay, what is this? This is V inverse times W naught times W naught times U. W naught is an involution, so this is just the same as the length of V inverse times U. Okay? But this is the length of U inverse times V inverse. And when you take the inverse of something, the length doesn't change, because you're basically reversing the reduced words. So this is the same as just the length of U inverse V, which we said is length of V minus length of U. But I could write this as, let's say, length of W naught minus length of U minus the length of W naught minus the length of V. Okay, so these are clearly the same thing. And the length of W naught minus U is the same as the length of W naught times U. So this is one of the facts about like how the length changes when you multiply by W naught. So length of W naught minus U is just the length of W naught U. And similarly, this is the length of W naught V. So what this shows is the length of this thing inverse times this is the length of this minus the length of this, which according to my equivalent reformulation of the right weak order is saying that W naught V, so W naught V is less than or equal to, in the right weak order, W naught U. And so we've shown that multiplying by W naught just reverses the right weak order, right? So U is less than or equal, if U is less than or equal to V, then W naught V is less than or equal to W naught U. And I mean, this is an if and only if, because I could just go in the reverse by multiplying by W naught again. Is that good? Okay, so maybe I should just state something that is useful to keep in mind, which is not too difficult, but it's sort of just good to have in mind. So I'll state this as a proposition. So for W and W, and a simple reflection S, the following are equivalent. The first is that S is a left descent of W. Again, remember this means that it's a simple reflection, so that if you multiply W on the left by S, then the length goes down. 2 is that S is less than or equal to W in the right weak order. And the third is that there exists a reduced word for W that begins with S. Okay? So proof. Any questions about the statement? So 2 and 3 are equivalent basically just by the definition of the right weak order. Right? The right weak order says that S is less than or equal to V if you can find a reduced word for W that has a reduced word for S as a prefix. Well, the only reduced word for S is S. So this is if and only if you can find a reduced word for W that begins with S. So 2 is equivalent to 3 by definition of the right weak order. So now for 3 implies 1. So let's assume that we have some, let's say S times S1 dot 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 SK, which is a reduced word for W. Then
Thank you.
I can write S1 through SK. This is S times W. So the length of SW is at most K. Actually, it should be equal to K. But all we need is that it's at most K. This is less than K plus 1, which is the length of W. Right, because if this is a reduced word for W, then W has length K plus 1, because this is a word of length K plus 1. So we get this. And that is the same as saying that S is a left descent of W. And then on the other hand, 1 implies 3. So suppose S is a left descent of W. Let's let S1 prime through SR prime be a reduced word for SW. then, if I just add an s to the front of that, this is a reduced word for w. That begins with s. Okay? Any questions up to here? Today is a lot of writing. Okay. Yes?
For y2 implies 3,
Mhm.
did we do that yesterday? Or sorry, last something because it's not immediately clear to me why it followed. Because I know we.
Why 2 and a 3 are equivalent?
Yeah, I mean, I know we stated those
So-
both as definitions, but it's not clear to me from like the v equals like ux definition. Why?
So the definition, I guess, well, in that way, would just be saying that, so you want to assume that, which direction do you want to go? 2 implies 3?
Yes.
So assume that s is less than or equal to w, then w is sx for some x, where the length of w equals the length of s plus the length of x. But then in that case, if you just take a reduced word for x and you add an s in front of it, that'll give you a reduced word for w that begins with s.
Sorry, please.
Yeah, sure. Okay. So here is another proposition. If u is less than or equal to v in the right week order, then I can consider these two intervals in the right week order. One is the interval between the identity element and u, and I'll write like interval sub r to mean, or wait, sorry, maybe, no, that's not what I want to write, sorry. U comma v is what I want. So this is the interval between u and v in the right week order. And I can also consider the interval between the identity and the element u inverse v, again in the right week order. And the claim is that these are isomorphic as posets. Okay. And the reason is pretty simple. Basically, the isomorphism is given by multiplying by w. So for the proof, like you can kind of think of multiplying by w as like translating one interval up to the other interval. That's essentially what's going on. So we will show that the map f from this interval to this interval is, or sorry, given by f of x equals ux is a poset isomorphism. So first of all, I want to show that this map actually has the correct codomain, meaning it actually maps this interval to this interval. So what I'll write is we have length of V equals the length of U plus the length of U inverse V. This is just because, again, U is less than or equal to V in the right week order, so that's what, equivalent to writing this. And this is less than or equal to, and let me label this less than or equal to with A, so I can refer to it later. This is less than or equal to length of U plus, so I have some X here, plus length of X plus length of X inverse U inverse V. Okay, so all I'm saying is that in general the length of U inverse V should be less than or equal to the length of X plus the length of X inverse times U inverse V. This is just because if I have a reduced word for X, and I take a reduced word for X inverse U inverse V, and I just put them next to each other, I concatenate these words, that gives me some word for U inverse V. It might not be reduced, but if it's not reduced, I can just make it shorter to get a reduced word for U inverse V. So that means the length of U inverse V is less than or equal to this. Okay? So we have this, and length of V is less than or equal to the length of Ux plus the length of X inverse U inverse V. So this is for the same reason that if I had a reduced word for Ux and I had a reduced word for X inverse U inverse V, I could put them together to get some word for V. Let me label this with B. And this is less than or equal to, and I'll label this one with C, length of U plus length of X plus length of X inverse U inverse V. Right, so that's because the length of Ux is less than or equal to the length of U plus the length of X. Again, by the same argument. So now, we can say X is less than or equal to U inverse V in the right week order, if and only if. Well, what would this say? This would say that the length of X inverse U inverse V equals the length of U inverse V minus the length of X, which would say that this is actually an equality. Okay, so this here is equivalent to saying that A is an equality. I'll just say equality in A. But okay, we'll notice that here A is length of V is less than or equal to this thing. But here I have length of V and I have the same thing over here. So A is an equality if and only if B and C are both equalities. So this is if and only if we have equality in both B and C. And what is this equivalent to? Well, having equality in B is the same as saying that that Ux is less than or equal to V in the right week order. And having equality in C is equivalent to saying that U is less than or equal to Ux in the right week order, because you want the length of Ux to be equal to the length of U plus the length of X. That's the same as saying this. Okay? So what is another way of writing this chain of equalities? This is just saying that x is in the interval between the identity and U inverse V. That's what this means. If and only if Ux is in the interval, or maybe I should say Ux is really what I was calling f of x, is in the interval between U and V. Okay, so this shows that this map F does actually map into the correct set, and it's obviously a bijection, well, just because this is if and only if, but like the inverse of this bijection is multiplying by U inverse. So we know now that F is a bijection from this set to this set. And just now we need to show that it's a poset isomorphism, which just means we need to show that it preserves the order relation. Okay, so I'll just say note F is a bijection. So now, if I take, so for x, y in this interval from E to U inverse V, I'll just say a similar argument shows that x is in the interval between E and Y if and only if Ux is in the interval between U and Uy. Right, it's basically the same argument as over here. But now, we can say, so if x is less than or equal to y in the right weak order, well, that's what this means. X is in this interval between the identity and y. So that implies that Ux is in this interval. So in particular, Ux is less than or equal to Uy. U is less than or equal to, or sorry, Ux is less than or equal to Uy in the right weak order. And so this means that it's a poset homomorphism, and so actually it's a poset isomorphism. Yeah. Okay. Well, okay, I guess oh, maybe I also have to show the reverse, but that's similar. Okay, so you just yeah, okay, so if Ux is less than or equal to Uy, then Ux is in this interval, so x, yeah. So actually I should write if and only if. There, now we're good. Okay, any questions up to here? Okay, so now we can actually finally combine the lattice stuff with the Coxeter group stuff. So let me start by defining a complete meet semilattice. Actually, maybe I'll just do that here. So a poset, or so, let me do this. A meet semilattice is a poset L such that every finite subset of L has a meet. And remember, meet just means it's a unique greatest lower bound. And a very similar definition is where we remove the finite condition, and this is called a complete meet semilattice. So a complete meet semilattice is a poset L such that every not necessarily finite subset of L has a meet. So same definition except remove the word finite. Okay?
Colin, why don't they say meet complete lattice?
A what?
A meet complete.
Oh, a meet complete.
Like what does semi do there?
Oh, the semi is you don't have joins.
Oh.
Yeah. Right, so a lattice would be that you have meets and you have joins, but a semi-lattice is like you only have meets. There's also a notion of a joined semi-lattice, which is where you only have joins. Okay, maybe I'll make one remark, which is that, so remember we talked about the Bruhat order. The Bruhat order is not a meet semilattice. And it's easy to see this just in, let's say, S3, because remember this is what the Bruhat order looks like. And if I just choose, say, this element here, well, it has 3 lower bounds, but it doesn't have a greatest lower bound. There's no lower bound that's bigger than all of the other lower bounds. So Bruhat order is not a meet semilattice or a joined semilattice or a lattice or anything like that. But the nice thing, which is one of the really nice properties of the weak order, is that it is actually a complete meet semilattice. Weak order which is the poset W with the right weak order, is a complete meet semilattice. I don't know if I have time to go through the whole proof. This is one of the longer proofs that we're going to go through, but I think it's a really important theorem, so it's worth going through. But I can at least start and hopefully get close to the end, if not to the end. Okay? Okay. So actually, I'm not going to prove that it's a complete meet semilattice. I'm just going to prove that it's a meet semilattice, meaning that I want to show that every finite subset has a meet. And then there's this thing, which is in the book, which I'm not going to go into, called the descending chain condition, and you can use that to then prove that it's actually a complete meet semilattice. But here we're just going to prove that every finite subset has a meet. And in order to prove that every finite subset has a meet, it just suffices to show that any two elements have a meet, because the meet operation is commutative and associative. So once you know that two elements have a meet, then if you have any subset, you can just repeatedly take meets among them to get any, to get the whole set. Okay, so proof. Suppose x and y are two elements in W. We will show that x meet y exists. And the proof will be by induction on the length of the element x. So I'm going to let E be the set of lower bounds of x and y. Or in other words, I can just write this as the intersection of this interval with this interval. So it's the set of things that are less than or equal to x and less than or equal to y. So first of all, if E is just the identity element, then we're done, because then the identity element is the only lower bound for x and y, so it has to be the greatest lower bound for x and y, so it's their meet. So in this case, E is x meet y, so we're done. So we may assume that E is not just the identity. So we're going to pick some element z in E of maximum length. And we're going to show that this is actually the meet. So what we need to show, so we need to prove that W is less than or equal to Z in the right weak order for all W in the set E. Right, E is the set of lower bounds for x and y, so we need to show that every lower bound for x and y is less than or equal to Z. And that'll show that Z is the meet. Any questions up to here? Okay, maybe we can get through this. Let's see. So let's suppose that S is a simple reflection in E. And I want to let Z, so I want to pick a reduced word for Z, which I'll call S1 through SR. And I want to pick a reduced word for X, which I'll call S1 through SR, and then S1 prime through SP prime. Right, so because Z is less than or equal to X, because it's in E, right, so it's less than or equal to X, that means I can take this reduced word for Z and extend it to get a reduced word for X. And similarly, y I can write as S1 through SR, and then let's say S1 double prime through SQ double prime. And I would assume that these are reduced words. So first of all, if S is not less than or equal to Z in the right weak order, then so what does it mean for S to not be less than or equal to Z? This means that, hold on. Right, I'll just say by the exchange property, and then I'll explain this. I can write X as S times S1 through SR, and then S1 prime through some SI prime hat through SP prime. Okay, so what am I doing here? I'm saying I'm going to multiply X by S on the left. If S is not a right descent, or sorry, if S is not less than or equal to Z in the right weak order, that's equivalent to saying it's not a left descent of Z. So that would be a reduced word, but then I can multiply by S again to get back to X. And when you multiply by S again, you're multiplying by a left inversion of Sx. And the exchange property says that multiplying by a left inversion is the same as canceling some letter. So I'm canceling this Si prime. And I know that I'm not canceling one of S1 through SR, because if I did, that would imply that actually S was a right descent. Oh, sorry. Okay. Wait, what am I doing here? Oh, sorry. Okay. Let me take that back. S is less than or equal to X in the right weak order because it's an E. So it is a left descent of X. So when I take this word and I multiply it by S on the left, that will be, I can multiply it by S on the left and cancel one of these letters. That's what the exchange property tells me, right? Because S is a left descent of X, I can write this, okay? And I know that the thing that I canceled, this Si prime, was not one of the S1 through SR, because if it was, that would have meant that S is actually a left descent of Z, but I'm assuming it's not here, okay? And by the same argument, with X replaced by Y, I can say Y is S times S1 dot 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 SR, S1 double prime dot 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 SJ double prime hat through SQ double prime for some I and J. Okay, and I should say these are reduced because they have the correct lengths. So S times S1 through SR is in E. Right, this is because I've now shown that I have reduced words for X and Y, which have S1 dot 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 SR as prefixes. So S1 dot 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 SR is less than or equal to X in the right weak order, and it's less than or equal to Y, so it's a lower bound for X and Y, so it's in E. But this is a contradiction because the length of S1 dot 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 SR is, this is a reduced word, so this has length R plus 1, which is greater than R, and R is the length of Z. And I chose Z to be an element of E of maximum length. And now I'm saying this is an element of Z, or sorry, an element of E that has bigger length. So this is a contradiction. I don't know how enlightening this proof is. Yes?
In the right weak order, for every every reduced word for Z, does there always exist an X like that?
Sorry, for every reduced word for Z,
Does there exist an X, sorry, for, okay, so I understand that X is greater than or equal to Z.
yes.
So for every reduced word of Z, there exists a reduced word of X that takes Z as a prefix?
Yes.
Oh, so it's not some? reduced
Right,
word?
yeah, so okay, I guess it's some reduced word for X contains a reduced word for Z as a prefix, but also every reduced word for Z can be extended to a reduced word for X.
Oh, okay.
Yeah. Maybe I didn't say that, but those are, yeah, that's
Okay.
true. Okay, so what do we get from this? So from this contradiction, S is actually less than or equal to Z. Because we assumed S is not less than or equal to Z, we got a contradiction, so actually S is less than or equal to Z. Okay, I might be able to finish this, hopefully. If not, I'll just do it next time at the beginning. So now, let W be some element of E that is not the identity, which we know exists because we're assuming E is not just the identity. So I'm going to use this fact, which I will call star, which is that if S is a left descent of U, some element U, okay, and it's a left descent of some element V. For some elements U and V, if S is a left descent of both, that implies that U is less than or equal to V in the right weak order, if and only if SU is less than or equal to SV in the right weak order. This is because if S is a left descent of U, that means I can, well, okay. Like, okay, assume S is a left descent of both. Then when I have this, I can take a reduced word for U that begins with S, because it's a left descent. And then I can extend that to a reduced word for V. But then when I multiply by S, I will cancel the S at the beginning of the reduced word for U, and I'll cancel the S at the beginning of the reduced word for V, and I'll get a reduced word for SU as a prefix of a reduced word for SV. Does this make sense, or should I say more about this? Okay, so I will assume that this is okay. I'm going to write on this board because it's easier, and I'm racing against the clock. Okay, so let S be a left descent of W. So W is my element that I chose over there. It's in capital E, but it's not the identity. So it has a left descent. Then, so S is less than or equal to W in the right weak order. That's equivalent, again, by that proposition I just erased, to saying that S is the left descent of W. And W, because it's an E, it is less than or equal to X. And also I can get the same thing with Y. Okay? So this means that S is a left descent of X, and it's a left descent of Y. But also, S is the left descent of Z by the previous paragraph, because I said S is less than or equal to Z in the right weak order. So since the length of Sx is less than the length of x, this is what it means for S to be a left descent of x. We can use induction. Right, so we're inducting on the length of x. This is an element of length less than x. So Sx meet Sy exists. So let's give it a name. Z prime. So by star, okay, so I'm using star but with U being X and V being Y. So this thing, where I'm saying S is a left descent of X and it's a left descent of Y. So I can plug this in and say that SW is less than or equal to Sx, and SW is less than or equal to Sy. Wait, is that what that gives? Maybe I want to do it with W. S is the left descent of W, so maybe I want this with V equals W, and that gives this, but then similarly if I do it with U equals Y and V equals W, then I get that. So SW is less than or equal to Z prime, because I've shown that SW is a lower bound for Sx and Sy, but Z prime is the greatest lower bound of Sx and Sy, so SW must be less than or equal to Z prime. Okay, I'm pretty much out of time, so there's like just a few lines left. Maybe the best thing is just to pick this up next time. But yeah, I don't want to go over time, so I'll just say we will finish next time.